In our previous lecture, we studied the concept of compactness and connectedness. We have seen this concept in calculus and also in analysis courses. The concept that we are going to introduce in this lecture are kind of new. So in this lecture, we are going to introduce a new concept such as first countable space, second countable space, Lindelöf space. The concept of this kind of spaces we have not seen in our previous courses, like in calculus, analysis. The concept of this new space depends on a more deeper study of topology itself. So let's begin with the definition of first countable space. In order to define first countable space, we need to define a countable space at the given point in a topological space. So let's define the countable basis at the given point in a topological space. So here is the formal definition for a countable basis at the given point in a topological space. A space X is said to have a countable basis at X in X. A space X is said to have a countable basis at this point X in this topological space X if there is a countable collection, script B of neighborhoods, if there is a countable collection script B of neighborhoods of X such that each neighborhood of X contains at least one element, contains at least one of the elements of script B. Okay, so a topological space X is said to have a countable basis at this element X in this X if there is a countable collection of neighborhood of X. Let's call that countable collection is a script B, such that if we pick any neighborhood of X, that neighborhood contains at least one of the elements of a script B. Then X is said to have a countable basis at X. And if the topological space X has a countable basis at each point of this topological space X, then X is said to be first countable space, or it satisfies first countability axiom. A space that has a countable basis that has a countable basis, a space that has a countable basis at each of its points is set to satisfy the first countability axiom, or the space is said to be first countable. If the space has a countable basis at each point of that space, then that space is called the first countable space, or we say that space satisfies the first countability axiom. Now let me give you example of first countable space. Every space, every topological space X with a discrete topology, is first countable. So if we consider any topological space X with discrete topology, then that space is first countable. This is quite obvious. So if X is first countable, if this space X is first countable, then by definition it has to have countable basis at each point in this space X. So to see this one, to prove why topological space with discrete topology is first countable, so let's see a quick proof here. So for this, let's suppose, to show this one, suppose this X is an arbitrary element in this topological space X. Now to show X is first countable with the discrete topology, we need to show that this X, topological space X, has a countable basis at this point X. And we know that in discrete topology, if you have a discrete topology, those singleton set, they are open, and this singleton set, not just the open set, is also a neighborhood of X, because neighborhood means a neighborhood of point means it's an open set containing that point. So obviously this is open set and also contains X. So if we pick any X in X, and if you have a discrete topology, this singleton set is a neighborhood of X, then this singleton set itself, if we just consider the collection of this singleton set, just the collection of one singleton set, then this collection, since it has just only one element, so is obviously countable. Then this collection, the collection of just one singleton, is a countable collection of neighborhood of X. And also if we pick any neighborhood of X, then that neighborhood will contain this singleton set, because singleton set just has X, and if you have a neighborhood containing X, or by default this singleton set is going to be a subset of that neighborhood, or this singleton set will contain in that neighborhood. So this collection satisfy the condition for the countable basis, so that this collection of one singleton set will serve as a countable basis for X at X. Then this collection is a countable basis at X in X. Since X is an arbitrary element, so we found the countable basis for we found the countable basis for this topological space at X. So that means X is so X is first countable. The topological space X is first countable. So here we have just seen that every topological space with the discrete topology is first countable space. Next, I'm gonna give you a definition of a second countable space. So here's the formal definition of second countable space. If a topological space X has countable basis, has a countable basis for its topology, it's a countable basis for its topology, then X is said to satisfy the second countability axiom, or X is said to be second countable. Okay, so here's the definition of second countable space. A topological space X is said to be a second countable space if there is a countable basis for its topology, and if your space is second countable, then we say that X satisfies the second countability axiom. So the difference between the first countable space and the second countable space is, for the second countable space, you have to have a countable basis for the topology of your topological space. But for the first countable space, for the first countable space, we don't have to have countable basis for the topology. Instead, you have to have a countable basis at each point in the topological space. Okay. All right. Now, from the definition, we can see that second countable spaces are first countable. Okay. So we can write down as a note. This is quite obvious. If your space is second countable, then it is also first countable. Or second countable space is first countable. Every second countable space is first countable. Proof is quite easy. Let me give you a quick proof. Suppose X is a second countable, and we want to prove this space is also first countable. Since X is second countable, so there is a countable basis for its topology, and let script B be a countable basis. Since if X is second countable space, then it should have at least one countable basis for its topology. Let script B be a countable basis for its topology. Since we want to show that X is first countable, that means we have to have countable basis for each point in X. So suppose X is an arbitrary point in X, or X is an arbitrary element in the topological space X. This script B is a basis. Okay, now here script B is a basis. By the definition of basis, every point of this topological space, it has to be in at least one of the element in your basis. the element x, which we have taken here, that's gonna be in one of the, it's going to be at least one of the element in script B. So if there is just only one element in script B containing this x, then we can just take that element as a countable basis for x. If there are more than one element containing x in script B, then we can take all of them, and the resulting subset, or the resulting collection is obviously going to be countable, because script B itself is countable. It has a countable number of elements. So if you take the subset of countable set, then the result is obviously going to be countable. Okay, that's why this is how we can find the countable basis for x at each point. Just let me write down this thing. The subset, suppose x is in x, then the subset script B prime of script B containing of those elements, the subset script B of B containing the subset script B of B containing x is countable. So basically in script B, we are taking only those elements of script B. In script B prime, we are taking only those elements of script B which contains x. Since script B itself is countable, so the subset of countable set is countable. That's why script B prime is also countable. It's countable. Thus, the subset script B of script B containing x is a countable basis. At x, lowercase x. Okay, thus x is first countable space. So here we have just seen that every countable space is first countable. Now let me give you a couple of examples of second countable space. So here's the first example. Let's consider the set of real line with the standard topology. So standard topology means all the open interval, or all the basis elements, they are open interval. Okay, if you are considering R with the standard topology, every open set in R, or every basis element in R, they are simply the open interval. Now consider R with the standard topology, and then this R with the standard topology is a second countable. So if it is second countable, then we should find a countable basis for the standard topology in R. Okay, now let's consider this collection. The collection, let me call that collection is script B, which is the collection of all those open interval. This is the basis element for the standard topology, which you have seen before. Now here we are taking those intervals, open interval, whose endpoints are the rational number. We know that the set of rational number is countable. So since the endpoint of our interval, which are obviously the basis element for the standard topology, so these intervals, since A and B both are rational numbers, so the collection of those intervals is obviously going to be countable. It's countable. It's countable because the endpoint of our intervals are a rational number, It's countable, and it's obviously, and is this collection is also a basis, because we are just taking the collection of open interval, and the basis for the standard topology is just the collection of open interval in R. Is a countable and a basis for the standard topology. Basis for the standard topology is the basis for the standard topology on R. Thus, R is second countable. Okay, so R is second countable. But remember, we are taking the standard topology here. Whether the space is going to be second countable or not, it depends on what topology you are taking. So in this example, in our first example, we took the standard topology on R, so R is second countable. But if we take if we consider R with discrete topology, then it's gonna be is not going to be second countable, which you can see in this example. Consider R with the discrete topology. Remember, in discrete topology, every singleton they are open. Then if we consider R with this discrete topology, then R is not second countable. If it is not second countable, that means R doesn't have or every basis of R for the discrete topology, they are going to be uncountable. Okay, if R has at least one basis for the discrete topology which is countable, then R is said to be second countable. But here we are saying R is not second countable. That means every basis for discrete topology on R they have to be has to be uncountable. And we know that if you are considering the discrete topology, then the collection of the open set in R is going to be a basis for the discrete topology if and only if that collection contains all the singleton set. Okay, just let me write down this result. You guys have seen this result in one of our previous lecture. Then R is not the second countable since or because the collection script B is a basis. It's a basis for the discrete topology. It's a basis for the discrete topology if and only if that collection script B contains all singleton set. That means a collection script B is going to be a basis for the discrete topology if and only if it contains all the singleton, which implies that the basis for the discrete topology, any basis for the discrete topology contains all the singleton. Since R is not countable, or the set of real number is not countable or is uncountable, or is not countable, the singleton sets are also non-countable or uncountable. And since this basis script B contains all the singleton, and since all the set of singletons are uncountable in R, so script B is also uncountable. Okay, So this implies that thus script B is uncountable, is not countable, okay, is not countable. So here we have seen that every basis for the discrete topology is topology on R is uncountable. That's why R, the set of real number with discrete topology, is not countable. Sorry, it's not a second countable space. But R with the standard topology is a second countable space. So you can see the same set. Sometimes it's gonna be second countable. Sometimes it's not going to be a second countable. It depends on which topology you are taking on that set. Now I'm going to give you a couple of more definition. Then we're done with this lecture, and one of them is the dense subset of a topological space. A subset A of a topological space X is said to be dense if the closure of A is X itself. If A is a subset of a topological space, and if the closure of that subset is a whole topological space, then that topological space is then that subset is called dense. It's said to be dense in X. Example, we know that we have seen in one of our previous lecture the set of rational number which we denoted by Q. The closure of Q is the set of real number. So we have seen that result in one of our previous lecture. So we can say that a set of rational numbers or Q is dense in R. Q, which is set of rational number, is dense subset, or is simply dense in R, is a dense subset of R since Q, closure of Q is R itself. Okay, let me add one more definition. So I'm gonna give you a definition of a separable space. So here is a formal definition of a separable space. A topological space X is said to be separable. It's said to be separable if it contains a countable dense subset. So if you have a topological space, if there is a topological space that has a countable dense subset, then that topological space is called separable. Now here we if you remember, I think it was in section 23, that was about the connected space. So we have introduced the concept of separation in that lecture. It was about the lecture for connectedness. So please don't be confused with the wording separable and separation. Separable and separation, there are two different things. Okay, separable is not same as the separation. So don't be confused with separation that we introduced in one of our previous lectures. Separation and separable spaces, they are two different terminology. Here is an example of this separable space. Uh, we we have seen that Q, which is the set of rational number, is dense in R, and obviously you also know that the set of rational number is countable. So we can say that R has a countable dense subset which is Q. Thus R is separable. And again we are considering the standard topology on R. R with standard topology, is separable because it has a countable dense subset Q. Okay. Again, so we are considering the standard topology on R. Now we're going to introduce one more type of space, which is called Lindelöf space. Then we are done with this lecture. So I'm gonna give you one more definition and example. Then we're done with lecture. A space X for which every open covering contains a countable subcovering. A space X for which every open covering contains a countable subcovering is called a Lindelöf space. So if you a topological space is called Lindelöf space if every open covering, it says every, okay, every open covering of X contains a countable subcovering, okay. And you guys have seen something similar definition of compact space. For the compact space, what you have to have, every open covering just have to have a subcovering. It doesn't have to be a countable. But for the Lindelöf space, every open covering should have a countable subcovering. Then the space is called Lindelöf space. So you can see the Lindelöf space. The condition for Lindelöf space is more stronger than the condition for compact space. Now let's see the relation between second countable space and Lindelöf space. So this, I'm going to give you a theorem without proof, and this theorem will give us the relation between second countable space and also the Lindelöf space, and also the relation between the second countable space and the separable space. And here is the statement of our theorem. Suppose that X has a countable basis. That means our space, topological space X, is second countable. Then the following two conditions are always true. Every open covering of X contains a countable sub-collection covering X. So which is basically the condition for the Lindelof space. So if you have second countable space, then it's going to be Lindelof space. And the second condition is there exists a countable subset of X that is dense in X. Okay, so this theorem, it gives us the relation between second countable space and Lindelof space. So every second countable space is Lindelof space. Let me give you an example. So we have seen that R, the set of real line with the standard topology, is its second countable. I think that was one of our example earlier. So that means R is also Lindelof space by this theorem. The real line R with the standard topology is Lindelof space, since it is second countable. So you can see here R is a Lindelof space, and like I said earlier, the definition of Lindelof space and compact space are something similar. I mean, it's not exact same. For the Lindelof space, every open covering should have countable subcovering, and for the compact space, every open covering should have finite subcover. Okay, we have seen that R with the standard topology is not compact, but R with the standard topology is a Lindelof space. That's why the condition for the compactness is stronger than the condition for Lindelof. For the compactness, you have to have finite, but for the Lindelof, you just need the countable. Okay, it doesn't have to be finite. That's why the condition for compactness is a more stronger than the condition for Lindelof space. I think little bit earlier I said that condition for Lindelof space is stronger than the condition for the compactness, but that's not true. I think sorry for that. Remember, the condition for compactness is more stronger than the condition for Lindelof space.